Predicting students' employability in engineering and MCA programs in India is a complex task, particularly when dealing with unbalanced and multidimensional educational data. To address this challenge, a novel cluster-based model is proposed for variable selection, which is integrated with improved predictive algorithms. This approach enables the identification of key attributes that significantly impact employability, moving beyond traditional academic metrics. The study underscores the importance of considering secondary attributes, such as communication skills, family background, and extracurricular activities, in addition to primary academic data. These non-traditional factors are often overlooked in employability predictions, despite their significant influence on a student's career prospects. A unified model adaptable across different institutes is essential, given the customized nature of teaching learning systems. The proposed model aims to provide a standardized framework for educational institutions, enabling them to guide students more effectively and improve their employability outcomes. By leveraging educational data mining techniques, this research offers a comprehensive approach to employability prediction, highlighting the interplay between academic and non-academic factors. The findings of this study have significant implications for educational policymakers, institutional administrators, and students, providing valuable insights into the complex factors influencing employability in the Indian context. Predicting student employability using data mining techniques is the primary focus of this study. A dataset of 8,973 student records from various Indian universities, comprising 152 attributes, is utilized. The multidimensional and unbalanced data, with few records of students placed in top companies, presents a challenge. To address this, RapidMiner Studio Academia version 7.1.001 is employed to apply various data mining algorithms. Initially, predictive algorithms were applied to the raw dataset, yielding unsatisfactory results. To improve performance, a clustering model was integrated at the preprocessing stage to reduce dimensionality. Comparative results demonstrate a significant enhancement in performance when clustering is applied before predictive algorithms. The literature review highlights the growing interest in predicting academic performance and employability using data mining techniques. Previous studies emphasize the importance of incorporating cognitive, psychometric, background, and academic attributes for better prediction. The need for large, multidimensional datasets with automated preprocessing is also stressed. Data mining, defined as extracting knowledge from large datasets, involves supervised and unsupervised learning methods. The model presented in this paper utilizes clustering at the preprocessing stage to enhance the performance of classification techniques. Techniques employed in the model include k-nearest neighbor, decision tree, random forest, and support vector machine. The experimental setup and results, presented with comparative analysis and charts, demonstrate the efficacy of this approach. The study concludes with scope for future work, emphasizing the potential of data mining techniques in predicting student employability. This section of the research paper discusses various machine learning algorithms used for classification, including k-nearest neighbors, naive Bayes, decision trees, neural networks, support vector machines, and linear discriminant analysis. The k-nearest neighbors algorithm searches for the k-training examples closest to a new instance in an n-dimensional pattern space, using a distance metric such as Euclidean distance. The classification is then determined by the most commonly occurring classification among these k examples. Naive Bayes classifiers, also known as probabilistic classifiers, apply Bayes' theorem with strong independence assumptions, considering all properties to independently contribute to the probability. Kernels are used in kernel density estimation to estimate random variables' density functions. Decision trees create a classification model that predicts the value of a target attribute through recursive partitioning, stopping when all examples have the same label value or when most examples have the same label value. Pruning is used to remove leaf nodes that do not add to the discriminative power of the decision tree. Neural networks, specifically the perceptron, are a type of artificial neural network that processes information using a connectionist approach to computation. A feed-forward neural network is one where connections among units do not form a directed cycle, and the information moves in only one direction, from input nodes to output nodes. The backpropagation algorithm is used to train the network, adjusting the weights of each link to reduce the error function. A multi-layer perceptron consists of multiple layers of nodes, with each layer fully connected to the next, and each node is a neuron with a nonlinear activation function, usually the sigmoid function. Support vector machines construct a hyperplane or set of hyperplanes in a high-dimensional space, which can be used for classification, achieving good separation by maximizing the margin between the hyperplane and the nearest training data points. Linear discriminant analysis tries to find the linear combination of features that best separates two or more classes of examples, and the resulting combination is used as a linear classifier. The experimental setup involves collecting data from various universities and institutes in India, with training and placement cells providing past records of students. The data is then compiled into a single spreadsheet. The data selection and transformation process focuses on engineering and MCA students, as they are more likely to opt for placements after obtaining their degree. The study's dataset comprises 8,973 instances with 152 attributes, characterized by its large size, imbalance, and multidimensionality. Following a level of preprocessing, non-essential attributes such as student names and phone numbers are excluded, while derived variables like age are calculated. Attributes are categorized and the dataset is numerically transformed for efficient clustering, referred to as ROAD. Predictors used in the study encompass personal, family background, academic, aptitude, and psychometric predictors. The RapidMiner Studio Academia version 7.1.001 is utilized to implement machine learning algorithms. K-means, fast clustering algorithm is applied with a numerical measure of Jaccard similarity, enhancing clustering performance. Various classification algorithms are employed for prediction, including Lazykin, Bayesian Bayes kernel, neural nets, perceptron, AutoMLP, neural net, support vector machine, libSVM, hyper, fast large margin, trees, decision tree, logistic regression, and discriminant analysis linear, LDA. A tenfold cross-validation technique is used to estimate classifier performance. Performance measures include classification accuracy, F1 score, and kappa statistics. Classification accuracy may not be a perfect indicator due to the dataset's large class imbalance, known as the accuracy paradox. F1 score is a weighted average of precision and recall, considering both false positives and false negatives. Kappa statistics measures the normalized value of agreement for chance. A novel approach is adopted for preprocessing the raw data, involving transposing the dataset by swapping attributes as instances and instances as attributes. The new dataset, RD1, is then clustered using K-means with Jaccard similarity, resulting in reduced dimensionality and improved classification performance. The cluster model involves 8 steps, including retrieving the raw dataset, transposing, applying clustering, filtering, generating new datasets, transposing data clusters, implementing classification algorithms, and validating performance with tenfold cross-validation. 11 predictive algorithms were applied to a dataset to predict students' employability, but initial results were unsatisfactory due to the dataset's complexity. To address this, principal component analysis, PCA, was considered as a dimensionality reduction technique, but it did not yield significant improvements. To overcome this challenge, a cluster model was developed, which involved applying K-means clustering with Jaccard's similarity to reduce the dataset's dimensionality. This approach significantly improved the results, as evidenced by substantial enhancements in F1 score and kappa values compared to the direct application of predictive algorithms. Statistical t-tests were conducted to validate these improvements, and the results indicate a significant difference in F1 score and kappa values between the two approaches, confirming the superiority of the cluster model. The application of K-means clustering with Jaccard similarity successfully reduced the dataset's dimensionality, leading to more accurate predictions of students' employability. The findings suggest that the integration of clustering techniques can improve the performance of predictive algorithms in complex datasets. The study's results reveal that the t-statistic surpasses the critical 2-tail value, indicating a significant difference in F1 scores between predictive algorithms applied directly and those using the cluster model. The cluster model outperforms direct application, showing a greater reduction in variance values. A comparison with principal component analysis, PCA, a well-known method for dimensionality reduction, demonstrates that the cluster model performs better than PCA when applied to predictive algorithms, with a significant difference in F1 scores and variance values. A paired two-sample t-test for means was conducted to compare the results obtained by predictive algorithms with PCA and the same algorithms with the cluster model. This test indicates that the cluster model surpasses PCA, with a significant difference in F1 scores and variance values. Furthermore, a comparison between predictive algorithms only and predictive algorithms with PCA shows that PCA does not perform better than the direct application of predictive algorithms, with no significant difference in F1 scores and variance values. To clarify these results further, kappa values are presented in Table 2, highlighting the significant difference in mean kappa values between the cluster model and PCA, as well as the predictive algorithms only. A paired two-sample t-test for means was conducted to compare the kappa values obtained by predictive algorithms with PCA and the same algorithms with the cluster model. The results indicate a significant difference in mean kappa values, with the cluster model outperforming PCA. Overall, the results demonstrate that the cluster model, when applied at the preprocessing stage with predictive algorithms, significantly improves the F1 score and enhances the performance of predictive algorithms to predict students' employability, even with complex datasets. Classifiers equipped with the kappa score demonstrate improved performance when integrated with predictive algorithms and the cluster model. In contrast, the application of principal component analysis, PCA, fails to yield enhancements. Statistical t-tests confirm the significance of these improvements, substantiating the efficacy of the cluster model. Notably, applying predictive algorithms directly, without PCA preprocessing, achieves comparable results to those obtained with PCA preprocessing. However, the integration of predictive algorithms with the cluster model yields a significant boost in kappa scores, underscoring the superiority of the cluster model in enhancing predictive performance for students' employability. These findings imply that the cluster model plays a crucial role in amplifying the accuracy of classifiers, particularly when combined with predictive algorithms. The kappa score, a metric that evaluates inter-rater reliability, serves as a robust indicator of the model's performance. The statistical significance of these results, as confirmed by t-tests, reinforces the validity of the cluster model in this context. The comparison between the cluster model and PCA highlights the limitations of PCA in enhancing predictive performance, suggesting that the latter may not be an optimal preprocessing technique for this specific application. In conclusion, the synergy between predictive algorithms and the cluster model offers a promising approach for improving the accuracy of employability predictions. The application of data mining techniques in predicting graduate employability has been increasingly recognized as a valuable tool for enhancing prediction accuracy. A multitude of studies have utilized various data mining algorithms, such as decision trees, neural networks, and clustering methods, to analyze factors influencing employability. These studies emphasize the importance of considering multiple attributes, including both technical and non-technical skills, to improve prediction accuracy. In particular, research highlights the significance of a comprehensive approach that incorporates both primary and secondary attributes. Primary attributes encompass academic performance, work experience, and specific skills, while secondary attributes include personal qualities, social skills, and extracurricular activities. By integrating these diverse factors, data mining models can provide more reliable predictions of graduate employability. The use of decision trees, for instance, allows for the identification of key factors contributing to employability. Neural networks, on the other hand, are effective in modeling complex relationships between attributes and employability outcomes. Clustering methods enable the segmentation of graduates into distinct groups based on their attributes, facilitating targeted interventions aimed at enhancing employability. Moreover, the integration of machine learning techniques can further enhance the predictive power of these models. For example, feature selection algorithms can identify the most relevant attributes influencing employability, thereby improving model accuracy and reducing complexity. Additionally, ensemble learning methods can combine the predictions of multiple models, leading to more robust and reliable employability forecasts. However, despite these advancements, challenges persist. Data quality issues, such as missing or biased data, can negatively impact model performance. Furthermore, the dynamic nature of the job market necessitates continuous updating of the data and models to ensure relevance and accuracy. In conclusion, the application of data mining techniques in predicting graduate employability offers promising insights into the factors influencing job prospects. By leveraging a comprehensive approach that integrates multiple attributes and advanced machine learning techniques, researchers and policymakers can develop more accurate models for predicting employability. This, in turn, can inform strategies aimed at enhancing the employability of graduates and addressing labor market needs.